Welcome everyone. So this is our 46th live stream geometry session. We have two people here with us today. And today I'm going to go over a couple problems from the Thailand IMO training. So I think in October they have a program where they train a bunch of people for the IMO. So I took a couple problems from there. And then the rest of them I took from just a couple mock olympiads, and the questions were given to me by one of the participants on this session. So with that, I'm going to share my screen. So here's the first problem I chose. I'm not sure if it's that hard, but it looked like an interesting problem. So let's see how quickly we can do it. So we have two circles with different radii, and then we draw the intersection of the common tangents. I kind of like these problems that have intersections of the common tangents because there's not that many of them. And so the common tangents intersect at H. So I'm going to hide some of those other points later. And then we have some point X, and we draw the two tangents to each of the circles. And if you connect, so we call it PQ, R, and S, and we're assuming PR passes through H. So what I'm going to do is, I think here's a better way to do it. So I'm going to draw, so if I draw these 2 points E and F, and I draw the tangents, well, actually, I'd really want to call them, it says PR passes through H. So I'm going to call this PR right here, P, and this is R. So this would be point X right here. I'm kind of reframing the problem a little bit. But so this is point X, and PR passes through H. So then the problem says if I draw the other tangents, then the line joining those should also pass through H. I'm going to draw that. So this would be Q. We have a new person with us. Let's see. So thanks for joining us, Manuel. So just to give you guys background, so he is a high school teacher from Peru. So thanks for joining us. All right.
Hello, everybody.
Hello. So, and now we have Hakan joining us. So yeah, good to see you. I actually had another person from Peru also email me that had his own YouTube channel this week. So I thought that was kind of cool. But maybe he'll come on the session sometime. So I'm going to hide a couple things here because there's too many lines. Actually, you know what? Before I do that, let me draw these points. And now I'm going to make the diagram look a little nicer. All right. Let me see what points I can hide. So I'll hide B and D and try to make these lines shorter. Okay. Oh, whoops, that didn't hide that much. So I'm going to hide this.
Actually, you cannot hide it that way. You should select it and then hide.
You're right. Okay. Oh, I think I have to hide it twice. I think that's the issue because I think I drew the tangent twice. So All right, so H is the intersection of the common tangents. And then from point X, we draw P, Q are the tangents to one circle, and R and S are the tangents to the other. And the problem says if PR passes through H, then we want to show that QS also passes through H. So it's kind of interesting. So PQ is the polar of X with respect to this circle, and RS is the polar with respect to this circle. Not sure how much that helps. Obviously, H, A, and C are collinear. Maybe we could use disargs because we have like 3 lines that concur.
Are EPRF cyclic?
Let's see. EP, R, and F. Yes.
Maybe inversion at H with reduce HE times HF squared.
Interesting. Okay, so we could try to use inversion because we know that that's cyclic. So that would swap E and F. It would swap P and R. It would swap I and G, right? We want to see if it swaps Q and S, basically. So,
but we know that IEFG is cyclic, and PRSQ is cyclic.
So yeah, maybe that's enough because we know that PQRS is cyclic. Is that obvious? Oh yeah, because all those tangent. Well, we know XP is equal to XQ, and we know XR is equal to XS.
Maybe the collinearity implies. I'm not sure.
Yeah, maybe it does. Okay, so yeah, because. Okay, I'm going to erase that circle for now, just because. But you might be right. It might just be that. Actually, let me move things around just to see if that's true. Yeah, I think the fact that they're collinear somehow means that all these tangents are equal. I don't know why yet. But that's what it looks like. Maybe we could let P, Q, and RS intersect. See. Did we prove? No, we didn't prove it.
Inversion proves it, actually.
Inversion proves that they're cyclic?
Yeah, inversion takes the circle with center A to circle with center C.
Okay, so basically the inversion is radius square, so HE times AF, so the square root of that. So yeah, and then that swaps those 2 circles. Okay. Is it so? The inversion, I see it swaps E and F. It swaps I and G. Is there one other point we can use to show that it actually swaps the whole circle?
They are tangent, so we don't need extra points, right?
I think it is homostatic, not inversion.
Okay.
Homotety takes P to another point, actually. Homotety is not enough.
So it swaps E and F, right? And it swaps I and G.
And because they are tangent, it swaps circles.
Okay, that's just like a well-known property.
Okay, no, actually, if you let H PR, homotopy. If you let HPR the line cut the circle A and C at two other points,
Okay.
so the homotopy from H will make A become C, right?
Yeah.
Yeah. So G will become R and P will become K. So by angle chase, we will prove that EPRF cyclic.
It's cyclic. Yeah. Because HEP is similar to HFK. So angle EPH equals angle FKR.
Yeah. And
which
that
is equal to
be,
EFR. Yeah.
Yes.
So yeah, we only need homotopy and yeah, Hakan just said it too. So yeah, we only need homotopy to show it's cyclic. But I don't know if inversion would help actually solve the problem. All right, we just have Daniel joining us. So thanks Daniel. I think it's Daniel. So let me know if. Hello. All right, so EFPR is cyclic. So I guess once we know that's cyclic, then we could apply that inversion, right?
Oh, actually, we could apply it in the beginning.
Or we could have applied it in the beginning. Yeah.
Yes, to see it, maybe we can use homotopy plus inversion to see why tangency and 2 points are enough.
Okay.
But I'm sure 2 points and tangency is enough.
Yeah. So X has the same power with respect to, or XP is equal to XQ. Let's see. Yeah, if we can show X lies on the radical axis, then I think that would solve the problem. So yeah, all four of these tangents are equal. This reminds me of another problem we did. So yeah, we want to show X lies on the radical axis. Maybe we can use the radical axis theorem somehow. So maybe by an angle chase, we could show XP is equal to XR by showing angle XPR is angle XRP. So that would be the same as showing, yeah, okay, it's just an angle chase because we can show that angle XPR is equal to XRP. Actually, I don't even know if we need to use that this is cyclic because
we will use the cyclicity after proving X is the center for radical axis.
Okay. So yeah, so basically, yeah, for the radical axis theorem. Okay. So I'm going to start typing it up, but yeah, that looks like the solution. Okay. Sorry. So I'll say, let me move, sorry. Let me move the diagram over a little bit. Okay. So I'll just say draw points J, K, G, and I as shown. And then by a homothety at H, triangle HEP is similar to HFK. HFK. Then, so we have angle EPH is FKH. And that is equal to angle FRK. And so that means that EF PR is cyclic. And then once we have that, now we can use an angle chase to show that XPR is XRP. So we have angle XPR. That's half of arc JEP because of the tangency. And then by similarity, arc JEP has the same measure as arc RFK. So maybe I'll say by the homothety at H, arc JEP is equal to arc RFK. So JEP is equal to RFK. And so we have XPR is half of JEP, which is half of RFK. And that is XRP. And so that means that XP equals XR equals XS is equal to XQ. And that means that RPQS is cyclic. Because X is the center of that circle. And so I'll draw that. And now we can use the radical axis theorem. So we have EPRF, PRQS, and
we must prove that SQEF are cyclic too.
Yeah, okay, so that yeah, I don't think we can use it right away. You're right.
Yeah, we will use angle chase to prove that. Okay, so we need to prove angle EQS plus angle EFS are 180, right?
Yeah.
So okay, so yeah. So
or we might be able to show that IQSG is cyclic.
that is the same, I think.
Yeah.
Yeah. I think I have done it on my diagram, but your diagram is a little different. So I need to look.
Okay, that's fine.
Okay. Okay. So angle EQS will be equal to angle EQP plus angle PQS, right?
EQS is EQP plus PQS, right?
Yeah, and PQS will be equal to SRK, right?
Okay.
So
And SRK is SFK. I don't know if that helps.
okay. So SRK will be a half of SK, right?
Mm-hmm.
Yeah, and we will go back to angle EQP, right? Angle EQP will be a half of it will be equal to angle EJP, right?
EJP.
Yeah, and that will be FRK, right?
Okay.
Yeah, and that will be a half of angle FK, right?
Mm-hmm.
Yeah,
Yes.
and so then we will have angle EQS will be a half of FS.
Yes, half of arc FS.
Yeah, and angle EFS is arc FS too. Yeah.
Okay.
Yeah, that will solve the problem. And so EF SQ are cyclic, and we will use the radical axis to prove that to 3 bond is collinear.
Okay. I think that makes sense. Hold on. So yeah, I understand the angle chase you just said. Serdar and Hakan are saying inversion can prove it. Trying to understand what they're saying though. So basically you're saying, so I think what her,
HQ intersect circle with center C.
yeah, so you're saying basically if we hide point X and we let's say we hit all these tangents, then basically you're saying if we let HQ intersect the other circle at S prime, you're saying by inversion PQ S prime R would have to be cyclic.
Yeah, but we use that X. We use X actually.
So but
Yeah,
I
we
mean,
use that XP equals to XR.
we use that XP is equal to XR. So I mean, yeah, we do eventually use it. So basically, if I hit X for now, that would imply PQS prime R was cyclic. But then since we know using X that it's cyclic,
Yeah, okay.
then S is S prime. That's kind of what you're saying, right? Okay. Hold on one sec. I think this might be because we just have HPQ is H K would be that angle. And then that would be the same as this angle. Yeah, okay. So yeah, really yeah, let me okay, let me do it like this. So if let HQ, I'll write it like this. Let HQ meet omega 2 at S prime and T prime. Then I want to show that S prime is equal to S, but then we would have angle HPQ is HKT prime. Okay. Which is, yeah, inversion would really give the same idea, but so HPQ would be HKT prime, which is RKT prime, which is RSQ. Or well, RS prime Q. And so so that means that HRS prime Q is cyclic, and that means that S prime equals S. So this is just like a backwards way of writing it. Okay. Let me see how Khan just wrote it. So yeah, I guess you're kind of assuming, yeah, it's obvious that two circles invert, or it's a well-known fact. Okay. I'll just leave it like this for now, but I like the way that you thought about it also. Yeah, so it's kind of well known that they invert to each other. So QS passes through H. All right. I liked all your ideas. They're all different ways of seeing it. Fung had an interesting way of looking at it where it's like half of arc FS plus half of arc FRS. But yeah, they all work. They all get to the same place. All right, so I'm going to move on to the next one. So here's a problem that Serdar proposed from this. I'm not sure if this is a mock contest, but looked interesting. So we have a scalene triangle with incenter I and circumcircle omega. So I is the incenter, and then we draw the circumcircle. And then we have a line passing through I. So any line passing through I not perpendicular to AI, and it meets AB and AC at E and F. J is the incenter of AEF. And then we draw the circumcircle of JEF. And it intersects the circumcircle at 2 points X and Y. and XY meets the perpendicular bisector of AI at K. And we want to show that KA is tangent to the circumcircle. Oh, by the way, thanks for joining, Animal. So let's see. So I'm going to hide a couple things. I'm not going to hide that just yet. So I want to draw AI, and I want to draw the midpoint of AI. So KA is equal to KI. I wonder if this is like a radical axis theorem problem. So yeah, so we have KA is equal to KI. So basically we want to show that KI is the power, KI squared is like the power of K with respect to the circle. So if we could show KX times KY is KI squared, that would be one way to do it. Let me try drawing the circle with center. The problem has to prove that yeah, so that is part A. Yeah, I didn't do part A yet. This almost looks like it passes through the midpoint of XY. I know I haven't done part A yet. I'm just playing around for now. Yeah, doesn't it look like it passes through the midpoint of XY?
You take the midpoint?
Actually, no, I don't think that's true. Whoops, sorry. Yeah, it's not, it shouldn't be the midpoint. Yeah. All right, I'm gonna close this. Oops. Yeah, I can do that. So let the circumcircle of AEF meet ABC. Oh, it looks like it might pass through that point. Let's see. Yeah, it does. Okay. So we have to prove that. Yeah, let's see if we can do part A.
Circle with center J. I'm not sure which.
Oh,
The circle.
in circle of AEF. So yeah, J is the in center of AEF.
So can you hide the circle of AEF?
Yeah, I can hide the circle. So yeah, AJ and I are collinear because they're both the angle bisector. Can I also hide the incircle of ABC? Yeah, I can do that. So first, yeah, can we show the two circles intersect at 2 points? I wonder, is this tangent? Are these tangent? necessarily. Not necessarily. Yeah, you can see it can intersect here.
It doesn't pass through G.
Yeah. So it looks like dk passes through G. We haven't proven that yet, but
It doesn't pass it through.
oh, it doesn't.
You just moved it and
Oh yeah, you're right. It doesn't necessarily. But yeah, is it obvious even that the two circles always intersect?
can you also hide G for now?
Yeah, I can hide G. Well, so Hakan said, if the line was perpendicular to AI, oh yeah, then the circle would be the mixed linear in circle. Yeah. So Hakan says AG, EF, and XY concur. Interesting. So I might let me check that.
It's trivial, but maybe it can be useful.
Just by the radical axis theorem. Yeah.
Well, BC doesn't pass through, right?
Or it's true by the radical axis theorem, right? But yeah, I'm not sure how much it helps, but should I leave it there? It's up to you guys.
BC doesn't pass through H, right? Can you check it?
What doesn't pass through H?
BC.
Oh, BC. I don't think so. No. Yeah, there's no way it could pass through H. So yeah, for now, I'm just going to assume part A, but maybe eventually we'll want to go back and prove it. So yeah, if the line was perpendicular to AI, then we'd get the mixed linear in circle. And if we tilt the line, so like, I wonder if that can help us prove
Or KI and BC parallel.
KI and BC. Let's see. I think they might be. Let me use the parallel line. Yeah. Yes.
It must be parallel to BC because if a KI is the tension, we use angle chase and it will be parallel to BC.
Okay. So yeah, if the problem is true, then that would mean KI would have to be parallel. Let's see. I feel like I've seen another problem that we did very similar to this. So KI, yeah, we drew like the parallels through I to the opposite sides. So Yeah, is there any way we can use like the in-center? Such that EXF equals EYF is 90 minus A over 2. So angle EJF. So yeah, I'm thinking, yeah. So like you said, if EF were perpendicular, then it would be the mixed linear in circle. But we want to show if we tilt it. Yeah, I'm not sure. Well, I think what we could try to do maybe is draw the mixed linear in circle. So let's say, and then compare the two. So yeah, I'm trying to find the best way to draw the mixed linear in circle. Okay, yeah, I'll delete those points for now. Yeah, so basically, yeah, when it's perpendicular, X and Y are the same point, and then we want to show that if we move it, that it becomes two points. So here it's tangent, and then if we tilt things slightly a little bit.
Can you draw the center of EJF?
Yeah. So yeah, what happens to the center of that circle? I don't know. K. Yeah, it looks like K is a fixed point. Yeah. So yeah, we could define K to be the intersection of the tangent at A to the parallel through I. Yeah, I like that. And then we want to show that K, X, and Y are collinear. Or so I'll call it K prime. So we want to show that K prime, X, and Y are collinear. So basically, actually, what we could do is we could just draw any line. Well, actually, maybe not. We could draw a line through K prime and let it intersect the circle at X prime and Y prime. And then we could draw this circumcircle of JX prime, Y prime and let it meet at E prime and F prime. And that's just, yeah, I won't do all that, but J Oh, I think you're right. Yeah, you're right. So basically K lies on the radical axis. I feel like we might be able to do stuff with point circles. So let's say we have the circumcircle of ABC, the point circle I, and oops, and this circle EFXY. We want to show that K prime lies on the radical axis of those three circles. So, well, it does. So what's the radical axis of EFXY and the point I? I wonder how you'd even do that.
I don't know. Maybe I can prove it.
Okay.
But the radical axis of the three circle. Okay, wait. So you call D is midpoint of AI, right?
Mm-hmm. Yes.
So when you let AI cut the circle JEF at 2 points.
Okay.
Yeah, it will be J in another point.
Whoops.
Yeah, so AI, J, and H will be what is it called?
Harmonic.
Harmonic. So DA square will be equal to DE square, DI square will be equal to DJ times DH, right?
Okay.
So D will be the radical, we rely on the radical axis of the circle point I and circle JEF, right?
Ah, okay.
But I don't know. Can we use it for? Oh, okay. So K prime is also lie on the radical axis of the circle point I and JF too, because the center of circle JF is lie on AI and KD is perpendicular to AI too. And the radical axis is perpendicular to the line of two center, right?
Yeah.
So K will so K will rely on the radical axis of circle point I and circle JEF, and so KX times KY will be equal to KI square will be equal to KA square, and that will solve the problem.
Or we could just use the radical axis theorem, yeah, because the circumcircle, this circle, the big circle, and the point I, basically K prime, by the radical axis theorem, KB, XY, and what's the other one? KD, XY. Oh, what's the radical axis of I in the big circle?
I don't think we can use the radical axis of Y in the big circle.
Okay.
So yeah. So let's say G is the center of circle JEF, right?
Mm-hmm.
So D is lie on the radical axis of JEF and the circle point I, right?
Mm-hmm.
DD. So the line through D that and perpendicular to IG will be the radical axis of circle point A and circle JEF, right?
Yeah.
Yeah. So and but K lie on that line. We define K as the point lie on the the point lie on the perpendicular bisector. Yeah.
So we have I, ABC, and JEF. Basically, K prime is the radical center of those three circles, right?
No. I don't think so. I don't think so we could use it. But we don't need a circle ABC.
Oh, we don't need circle ABC. Okay.
Yeah. So we just need KD is the radical axis of circle point I and circle JEF, and that's all.
That's all we need.
Yeah, and that is because what I have says, and through that KI square will be equal to KX times KY, and KI square also equal to KA square. So KA will be the tangent of circle ABC.
Okay, so, well, so should I use K or K prime to write up the solution?
K, not, we don't need K prime.
Okay.
Okay. And you will need KXY.
Okay.
Yeah, that line. Yeah.
All right. That's where I got confused. Okay, so hold on. Let me read what Hakan wrote just to see if he has another way of doing it. Consider the point circles A, I, and JEF. Their centers are collinear. So K lies on the radical axis of A and JEF. So Hakan, do you know if I'm just reading through your solution, did it work, or oh, you assume K prime writing that? Okay. Did it work though?
Both solutions are complete.
Okay. All right. I'm gonna do I'm getting confused with all this radical axis stuff, but okay, I'm gonna write up Feng's solution. So yeah, I think both are correct. So so Feng was saying that A, I, J, and H are in harmonic conjugation.
Yep.
And that's true.
Because J is the in center and H is the X center.
Okay. So or maybe I could write up both solutions actually. J is the in center of AF, and H is the X center, and so so JH, I, and A are in harmonic conjugation. And so D is the midpoint of AI. So that means that dj times dh equals di squared. So D has the same power with respect to the point circle I and this circle, so it lies on the radical axis. And then K, because it's perpendicular to DG, K also has to lie on that radical axis. And so, yeah. So D lies on the radical axis of the circles JEF and the point, I'll just say circle JEF and the point circle I. Let me break this up. So since DG is since G is the center, or IG, I'll say KD is perpendicular to IG, implies KD is the radical axis. So that means that Ki squared is equal to Kx times Ky. Which is equal to Ka squared. Oh no, we're trying to prove Ka's tangent. But if Ki squared is Kx times Ky.
And Ki squared is Ki squared too, because K is lie on the perpendicular bisector.
Oh, that's right. So we have Ka squared is equal to Ki squared is equal to Kx times Ky. And then that means that Ka is tangent to omega. All right, so this is the first solution. So let me look at what Hakan said. Okay, I'm just gonna look through it because so did yours avoid the harmonic bundle? No, you still had to use the harmonic bundle, right? Okay. All right, so I'm going to move on to the next one. This is a nice problem. I like it. Okay. This one looks a little harder. So we have a triangle ABC, and gamma is its circumcircle. And then we draw the tangent at A. And then we take 2 points on it that are the same distance from A. So call it D and E. So this is D and this is E. So I'm going to hide some stuff. And then we take the circumcircle of ABD and ACE. So we draw the circumcircle of ABD and ACE. we see where it meets the two sides. So this circle meets AC at F, and the other one meets AB at G. And then we draw the common chord of those two circles. I don't want to call it H because it's, I'll call it N. So then let me move the diagram just a little bit. So we want to see where does AN meet the circumcircle of ABC. Meets it at a point H. And then K is the reflection of H across BC. See where that goes. So this is K. And L is the intersection of BF and CG. And we want to show that AK and L are collinear. It almost looks like FG is parallel to BC, but I don't think that's true. Maybe it is. I don't know. Hold on, I'm going to read the chat in just a second. Let me hide this. And it looks like Ramakrishna Sen is joining. Hey Ramakrishna, thanks for joining us. Oh, AH is a symmedian. Oh, Sardar, you already saw it. I'm sorry. So yeah, maybe you could give us hints if we get stuck. But yeah, sorry, it shows a problem you already saw. So yeah, welcome Ramakrishna. So how do you know AH is a symmedian? Actually, how did you know all that? Or how do you know it suffices to prove AH is a oh, because if you take that symmedian point, you reflect it, then it's collinear. It goes to the median.
It only is true if you have a GF parallel to BC.
Okay, so basically we can prove that GF is parallel to BC, so that shows that AL is a median, and then if AH is a symmedian, then AK is also a median. Okay, yeah, so this is like a bunch of well-known facts combined together. But yeah, is it obvious that AH is a symmedian? I guess we still have to prove that. So yeah, we have to prove two things. We have to prove FG is parallel to BC, and then we need to prove that AH is a symmedian. And it's well known.
We used this fact in a previous problem.
Oh, I think you're right. Yeah, that was a previous video we did. So yeah, let's see how we can prove FG is parallel to BC. So yeah, we have to use that AD is equal to AE eventually. So angle AFG is angle AFB minus GFB. I don't know if that helps. So D and E both have the same power with respect to the circumcircle of ABC, right? So maybe that helps somehow. So yeah, is there any way we can use that? So let's see. They have the same power.
Okay, we have that triangle N
And BF is similar to NGC.
NBD is similar to NGE.
Okay, and NBD is similar to NGE.
Yeah. Because that is only the what is called
Spiral similarity.
Yeah, spiral similarity. So angle ENG will be equal to angle DNB, right?
Mm-hmm.
And that will be angle DAB.
Okay.
And that will be angle ACB, right?
DAB is, yeah, ACB.
Yeah, and if you call BC cut circle AEC at 1 point.
Okay.
So that that point. So angle ACI will be equal to angle ENG.
So
right?
ACI equals ENG.
Yeah. So so IG will be equal to AE.
Okay. So IG would equal AE.
Yeah, and as well as if you call ADB cut BC at 1 point.
Ah, okay.
So FG, yeah.
So yeah, IG equals AE equals AB equals FJ by the same argument. So that means FG.
No. That is not enough. As well as angle GIJ is equal to angle FJI. That is 180 minus angle BAC. Yeah. So two triangle GIJ and FIJ is equal to each other. So that's we'll have GF parallel to IJ.
Okay, I'm gonna write this up. So okay, so first we have by a spiral similarity at N, NBG is similar to NBE. Is that right?
No, NBD is similar to NBD is similar to NGE.
Yeah. So hold on. Let me think about that for just a second. So NBD is equal to NAE, which is NGE. Okay, so and yeah, so it's by spiral similarity or an angle chase. Yeah. Okay. So, and so we have angle, I think you started out by saying angle GNE is BND, right? I'm trying to remember. Then, so BND is BAD.
Yeah,
And BAD.
will be ACB.
Yeah. So GNE, BND.
BND, not BNA, Michael.
GNE is BND. Yeah, BND, which is BAD. Which is BCA. Which and BCA is
ICA.
Is ICA.
Yeah.
Oops, sorry. So GNE equals ICA. So what is that? What do we do from there? I forgot what the next step was.
Yeah. So arc AI will be equal to arc GE.
Oh, okay. So arc AI is arc GE. Yeah. So
arc GI will be equal to arc AE.
So that means AE equals GI. And then, so similarly, AD equals FJ. So that means that GI equals FJ. And so we know this. Now we have to show that these angles are equal. I'm guessing that's an angle chase. Because angle GIC is 180 minus angle A, which is angle FJB. Yeah, so combining these two, GIFJ is a trapezoid. GIJF is an isosceles trapezoid. And so GF is parallel to IJ. Okay, so this is the main part. So from a previous video, that means that AH is a symmedian. Implies that AH is a symmedian. And then at the same time, so and that implies that AK is a median. That's well known. then since GF is parallel to BC by Cheva on point L, or I should say BC here. So I'll just say by Cheva's theorem on point L, GF is parallel BC means that AL is a median. So AK and L are collinear. All right. So yeah, these, I think this fact is pretty well known that if you take the symmedian point and you reflect it over BC, so where the symmedian meets the circle, you get the median. Yeah, we use this fact from the previous video. Let's see. Yeah, I don't remember which one it was. I think, Serdar, do you have any idea? It was a while back. Let's see if we can think through it right now.
What do we need right now?
Oh, so we're trying to show that if GF is parallel to BC, then this implies that AH has to be a symmedian.
Well, the distances and AB and AC equals to the ratio of AB and AC. We used this in a previous problem.
Oh yeah, so basically you're saying that if you drop perpendiculars from N to AB and AC, then the ratios of those perpendiculars are AB over AC. Is that kind of what you're saying?
Yeah, because of the similarity.
Yeah.
NBG is similar to NFC.
Okay, I'll just write a little bit here. So you can prove this by showing the ratios of the perpendiculars from N to AB and AC is AB over AC. Okay, so that's how you prove AH is a symmedian. All right. So I'll move on to the next one. But yeah, we're only, let's see, was this our third problem? Yes. All right, so yeah, I chose 7 of them. Okay, so here's another one Serdar showed. This one looks a little bit easier. So AC is greater than AB. So yeah, I'll see if how quickly we solve this. So D is on AC such that CD is equal to AB. Oh, CD is equal to AB, sorry. So I could use the compass tool for that. It almost looks like D is the midpoint. Let me change that. So yeah, maybe that looks a little better. The angle bisector BAC intersects the circumcircle at M. So M is like the midpoint of arc BC. Sorry. I doubt DM is perpendicular to BC. There's no way. But yeah, it's not. Let the perpendicular bisector AD intersect AM at E. So this is going to be point E. And let F be the midpoint of EM. So this has to be like similar congruent triangles somehow. We want to show that FB is equal to FB. Interesting. So basically we want to show that F lies on, well, actually. So yeah, let me draw the midpoint of AB. Okay, so did I draw everything that I need? So D is that point, and then yeah, I think I drew everything I need. ABFD is cyclic, is equivalent. Because if FD, yeah, because that would mean the angle bisector meets the perpendicular bisector at F. So yeah, we basically want to show ABFD is cyclic. That's a good point. So yeah, how do we use the fact that CD equals AB? That seems like key to this problem. It almost looks like MD is not perpendicular to BC though. Yeah, you can see it like that. We could try to rewrite the problem by drawing a circumcircle of ABD. I think that might be easier. Like, what if we let the circumcircle of ABD meet AM at F prime? And then
Yeah, this seems easier.
yeah. And then we want to show FE is equal to F, we can call this F prime. And then we want to show F prime E is equal to F prime M. So MF prime times MA, that's the power of M with respect to this circle. Can we say anything about like,
And drop the perpendicular from M to AC.
yeah. We'll call it G. We'll call it K. So CD equals AB. Can we use power of a point somehow? So the power of C with respect to the circle is CD times AC, which would be AB times AC. Okay, so yeah, we want to show F as the midpoint of EM, or F prime is the midpoint of EM.
Are KC and AG?
I was wondering that. Are they equal? Let's see. So what I'm going to do to figure that out, looks like KC might equal AG. So I'm going to draw the midpoint of AC and the midpoint of KG. And it looks, yeah, it looks like they're the same point. Yes. So yeah, maybe I could just let L be the midpoint of AC. We know AD, and we can compute KC. Because AD is AC minus AB, right? And we can compute KC because angle CMK how do we compute KC? KC is AC minus AK. Yeah, that works. So I could try writing some of this out here. So KC is AC minus AK, which is AC minus AM cos A over 2, right?
I think we can prove it synthetically with
Synthetically.
drawing. Can you draw the center? Can you draw the circle with center M, which passes through B and C?
Yes.
And can you label the intersection of AC and its circle?
Yes.
Now we want to prove that FC equals to AD.
Mm-hmm. Which is the same as, I think, as saying that LM is equal to LA, which is, but wait, that would mean, that doesn't sound right.
That is obvious because AF is equal to AB. So FC will be equal to AD.
Yeah, he's right.
Yeah, F is the reflection of V over AM. So AF will be equal to AB. And DC is equal to AB too. So AD will be equal to FC.
Okay, I'm going to change this from F to a different name just because, okay. If you were saying AN is equal to AB, is that obvious? Oh, because it's an angle bisector. So yeah. So I'll just say label points N. So yeah, do we even need point L? So yeah, AN is equal to AB. Oh, really? It appeared on your, interesting. Okay, so AN is equal to AB and CD is equal to AB. So combining those, AB is equal to CN. And once we know that, AG is equal to GD is equal to NK is equal to KC. And so
we must prove that F prime A is equal to F prime C.
yeah.
If we call ADB cut AM at F prime, we need F prime A. If F prime A is equal to F prime C, so F prime L will be perpendicular to AC because L is the midpoint of AC. Yeah, and we need F prime C is equal to F prime A.
Okay. F prime C is equal to F prime A. That's what we want to prove. So did we solve for, just trying to think. So F prime A is equal to F prime C means that this angle, so we know that that angle is A over 2. We want to show that this angle.
I think it is obvious because the spiral similarity from B.
Okay.
Yeah, text D to C and F prime to N. So B M C. So let's say BF prime M is equal to BDC, right?
Okay.
So I think hold on.
Okay. Are we trying to prove? We're trying to prove. No, we proved that. We're trying to prove that F prime A is F prime C. So yeah, first I'll write out what we proved so far so you don't forget it. So since AM is an angle bisector, that means that AB equals AN. So that means that AB F prime taking AB to CD. Oh yeah, maybe we can show, yeah, triangle ABF prime I think is congruent to DF prime C. Yeah. Yeah, we can show they're congruent by side, angle, side. So, whoops, looks like Serdar just got kicked off. So, CD, so actually we can make this like the last step. We know, okay, so, but yeah, we can show by an easy angle chase that, yeah, F prime DC is congruent to ABF. So yeah, that makes it really easy. So first, I'm just going to write up the ideas in the problem. So let the circle ABB meet AM at F prime. And then basically, we have, so AB is equal to CD and BF is equal to F prime B. So AB equals CD, BF equals F prime B, and then the angles are also easy to see it's equal. So angle ABF is ABF prime is F prime BC. So that means those triangles are congruent. So triangle ABF prime is congruent to F prime BC. And so that means that AF prime equals F prime C. And then we also have this piece right here. So
we also used the AG equals to KC.
Yeah, so I'm about to show that right here. So yeah, since AM is an angle bisector, by symmetry, so actually I should just first write out what N is. So draw the circle centered at M through B and C. Let it meet AC at N. And then by symmetry, yes, since AN is an angle bisector, AB is equal to AN. And so since CD is equal to AN, AD is equal to NC. And so, yeah, AG is equal to KC. And from there, if AG is equal to KC, then does it follow easily that F prime is the midpoint of EM? I think it should. Because yeah, this because then that means that FG is equal to FK.
So so L will be midpoint of GK, right?
Yeah. Yeah, L is the midpoint of GK or AC.
If we call L is the midpoint of AC, so L is the midpoint of GK as well. And because FA is equal to F prime A is equal to F prime C, so F prime A will be perpendicular to AC, right?
Yeah. Yes.
So F prime L will be parallel to EG, so and parallel to MK, but L is the midpoint of GK, so F will be midpoint. F prime will be midpoint of EM.
Yeah. So let L be the midpoint of both AC and I think it was GK. Yeah. And then FL is perpendicular to AC, or so F prime L is perpendicular to AC. And then also F prime L is parallel to MK, which is parallel to GE. That means that F prime E equals F prime M. And that means F prime equals F. That means that FD is equal to FB. All right. Looks good. So I'll move on to the next one. Got 3 more that I chose. Oh, this is interesting. I don't know if you guys have seen this before, but I don't think I've seen it. So yeah, super short problem, right? So I'm going to relabel